Lesson 26, Demo. Today we learn the technique of implicit differentiation used when the equation for a curve is not written in the explicit y equals stuff with x format. Find an equation for the tangent line to the curve -5 equals -9x squared plus x squared plus y squared squared times x plus 2 at the point -1, 1. This curve is called a conchoid of Nicomedes. So let's take a look at this strange curve. It looks like two separate pieces, but they both come out of this thing. So we got this wild looking thing with like a vertical asymptote. On the top, it goes to infinity, but then on the same side, the right side of this vertical asymptote goes to -infinity, so not a function. And then we got like this like oval type thing, looks completely separate, but again, they both came from this one particular equation. So let's take a look at the point -1, 1 and plot that point. So -1, 1, I think that's there. And even though this particular curve is not a function, there is a tangent line to the curve at that one spot, isn't there? We could draw a tangent line. Looks like it's downhill, kind of steep. We'll try one more time on that one. Something like that. Okay, third time, we're gonna get this one perfect. Ah, excellent. So it has a tangent line, and we're going to find the equation of our tangent line. So even though it's not a function, we can do this new technique. So here we go. I've written the original equation out, -5 equals, but I've left a telling space in the front of both sides. And in that space, we're going to put d over dx. So all we're doing is taking a derivative of both sides. We've done this before. So if the two sides were equal before, then certainly after we take a derivative, they will still be equal. Okay, left-hand side is easy. Derivative of -5 is 0 equals. Okay, let's do the derivative of the right-hand side. The right-hand side is a big old sum. So over that plus sign, we're going to do two separate derivatives and then add. The derivative of -9x squared is -18x. But I'm going to do something kind of funky here. That's the end of this one. The derivative of -9x squared is just -18x. But pretend for 1 second that it wasn't simply x. Pretend it was some stuff, something more complicated than x, something with x's in it. Then we would say if it was like -9 times some stuff squared, the derivative would be -18 times the stuff, but then times the derivative of that same stuff, right? That's the chain rule. And so that's what I'm going to do here, even though it seems kind of silly because it's just x and the derivative of x is just 1, but I'm going to write it anyway. So it's a -9, the 2 comes down, so there's my -18. I copy the stuff once, subtract 1 from the power, so there's an invisible 1 power, and then times the derivative of the stuff. And the derivative of the stuff, the derivative of x, well, dx is just 1. But anyway, that's fine. That's the derivative of the stuff. Okay, coming back here, now we're ready to do the second part of our plus. Okay, and now we're doing the derivative of the rest of it, but the rest of it is a big old multiplication. So there's a product in there, and there's y's in there too, which is kind of frightening, but let's see what happens. So we do the product rule. First, we copy the first, times the derivative of the second. The derivative of x plus 2, it feels like it's just 1, right? But I'm going to go ahead and continue to do this kind of silly thing. It's really 1 times the derivative, it's really the derivative of x, right? 1 times the derivative of x with respect to x, which of course is just 1. That's the first part of the product rule, plus, let's do the rest of the product rule. Second, x plus 2 times the derivative of the first. Okay, so the first is x squared plus y squared squared. So that's some stuff squared, and the chain rule says the 2 should come down, and you copy the stuff 1 time. And you subtract 1 from the power, so there's an invisible 1 power, and then times the derivative of x squared plus y squared. So the derivative of x squared is 2x, but I'm going to continue to do this silly thing here. Plus, and then the derivative of y squared is 2y, but now I'm going to do the same thing, it's d dx of y, but that is not a silly thing, because y is a function of x. I mean, it's not a function, but you can imagine maybe by some miracle you could take this equation and solve it for y, and if you could do that, then you would have y equals some stuff with x in it. And then this y squared right here would really be just some stuff squared. And the 2 would come down, and you'd copy the stuff. And that's exactly what we did. 2 came down, we copied the stuff, it's called y. And then you'd multiply right here by the derivative of the stuff. and this stuff is called y, and so that's exactly what we did. And so it was silly for us to do all of these dx's over dx's, because dx over dx is just 1. But it was not silly, it was mandatory to do that dy over dx. And so I'm going to write this thing the way that I actually want you to write it. I don't need you to do all the details that we just did. Here's the takeaway. Any derivative involving simply x, you just do it as normal. And so the derivative of negative 9x squared is just negative 18x. I don't need to see. I can't get rid of that. Maybe it'll go away. Okay, so I don't need to see the times dx dx. I don't need to see this part right here. Any derivative with just x, you just do it as normal. But what I do need to see is that anytime you take a derivative of something with y's in it, you do your ordinary derivative, y squared becomes 2y, but then you multiply by dy dx. That's our shortcut. So let's go through this derivative calculation again using our shortcut. So I've got the original function at the top of the page here. So negative 18x plus. And so then we do our product rule. So first, times the derivative of the second. The derivative of x plus 2 is just 1. No need to put dx dx. Plus the second, x plus 2, times the derivative of the first, x squared plus y squared squared. The 2 comes down, copy the stuff, subtract 1 from the power, and multiply by the derivative of x squared plus y squared. Derivative of x squared is 2x. Derivative of y squared, this is the only thing that's different. It's 2y times dy dx. That's the chain rule. Technically, the chain rule is coming in on every derivative, but it's kind of silly to write down the chain rule when you're doing derivatives of things with just x, because dx dx is 1. So I'm going to put a blue line here and say I don't need you to do the stuff between these blue lines. You can just jump to the bottom one. Again, the punchline is when you take a derivative of something with x, it's just normal. But when you take a derivative of something with y, you do the ordinary derivative, follow the basic derivative rule, as if the y were an x, but then at the very end, the chain rule says multiply by dy dx. So that is the only new thing for implicit differentiation. Okay, so what are we trying to do here? So we're trying to find the equation for the tangent line. So it is possible to solve this equation right here for dy dx. We could do a lot of algebra to solve this equation for dy dx. I'll just say it, but I'm not going to write it. You'd add the 18x to both sides. You'd subtract this x squared plus y squared squared from both sides. Then all that would be left on the right-hand side is this. You were trying to get this by itself first, so you would divide both sides by x plus 2 times y squared plus y squared. Then on the right-hand side, all that was remaining was this. You would subtract the 2x. You would then divide both sides by 2y, and lo and behold, you would have dy dx equals some horrific mess. But you could get dy dx by itself. And in some problems, I will ask you to do that. But I'm not asking you to do it here. What I'm asking for is the equation of the tangent line. One other thing I'll point out here. If you went through that mess to get dy dx by itself, you would have dy dx equals, and there would be x's floating around that complicated expression, but there would also be y's floating around that complicated expression. And oftentimes with implicit differentiation, there's no getting around that. Every single derivative calculation we've done this semester has just been a formula involving x's, or whatever the independent variable was. But for implicit differentiation, the norm is that the derivative formula is going to have both x and y in it. Occasionally we can get away from that, but usually it's going to have both x and y. Okay, so what I'm going to do is say we're looking for the equation of a tangent line. To find the equation of any line, we need two things: a point, which we have, and a slope, which we don't. So we're going to find the slope right now by taking the negative 1, 1 and plugging in for all of these x's and y's. Negative 1, 1 means x is negative 1 and y is 1. So we're just going to do a whole ton of substituting here. Rewrite that black equation with lots of numbers in it. So negative 18 times negative 1 plus negative 1 squared plus 1 squared. The times 1, no need to write that, plus negative 1 plus 2 times 2, negative 1 squared plus 1 squared times 2 times negative 1 plus 2 times 1 times dy dx. And the goal is to get dy dx by itself. So essentially, we actually have to do all of the algebra that I said we weren't going to do before, where I just talked out loud about how we could solve this big equation for dy dx. But the nice thing is that it's much, much easier to do it here when we've got only numbers, because these numbers are going to clean up before we do any of our algebra. And the algebra will be much simpler at the end. Okay, 0 equals negative 18 times negative 1, that's 18. In the parentheses, be very careful, that is a positive 2, and it is being squared. Plus, the next parentheses is a positive 1, and there's a 2. It actually doesn't have parentheses for the 2. The next parentheses, again, is a positive 2. Be careful there. Next parentheses, I see negative 2 plus 2 dy dx. It already looks much better. Let's do some more arithmetic here. 0 equals 18 plus 4 plus 1 times 2 times 2, that's 4. You cannot combine anything in here. Don't try. Okay, and then this is 18 and 4 is 22, and then I'm copying everything here. Could distribute that 4 if you wanted to. Okay, and now trying to get dy dx by itself, I will highlight it. This is the thing that needs to become alone. So we're going to move everything else away from that. So we'll subtract 22 from both sides. I don't know what I just did, but it wasn't good. Negative 22 equals. Then we're going to divide both sides by 4. So 4 goes into that. I guess that's negative 5.5, right? Negative 5.5 equals negative 2 plus 2 dy dx. Okay, then we're going to add the 2 to both sides. So we get negative 3.5. Then we're going to divide both sides by 2. Again, we've been trying to get the dy dx by itself. So we divide both sides by 2, negative 1.75 equals dy dx. Hey, how about that? The slope of this tangent line is negative 1.75. Not scary, not a bad number. Take a look at this picture. Does it jive with that black tangent line? Is it possible that the slope of this black tangent line is negative 1.75? Sure. The way that I drew it, it kind of looks like it's right around negative 2, but maybe I made it just a little bit steeper than it should have been. You know, maybe like it should have been a little bit more like that. So negative 1.75, perfectly reasonable for that slope. And then we'll just do our standard mx plus b business. We just calculated the slope. The m is negative 1.75. Just have to do a little bit of work to find the b. Remember, the point that we were given was negative 1 comma 1. So we plug in and we get 1 equals negative 1.75 times negative 1 plus b. So that is a 1.75 plus b, and we subtract that 1.75 from both sides, and we get negative 0.75 is b. Let's see if that's reasonable. Does it look like the y-intercept of that black line could be negative 0.75? Sure. For me, again, it's off by a little bit. Looks like for me it's negative 1, but if you told me it was in actuality negative 0.75, I would have no trouble believing that. And so then the final answer is just the final equation of our tangent line, which is y equals negative 1.75 times the x is just x, and then plus b, which is a minus 0.75. So that right there is the equation of that tangent line at the point negative 1 comma 1. All right, so on the next page, it says if there's time, we're going to use Geogebra to check our tangent line, and we could maybe even play with some sliders to graph this thing, which is a more general version of the equation we started with on the previous page. Okay, so let's go back for a second here. So our equation, I just tried to change some of these specific constants to letters. So a instead of negative 5, b instead of negative 9, and c instead of 2. Let's play around on Geogebra. So here is a blank Geogebra worksheet, and we are just going to see if we can get some space. All right, so I am going to make some sliders here. So slider, I just click this button and I click anywhere in the blank, and it says, okay, we're going to call this slider A, and it's going to range from negative 5 to 5. I'm going to go ahead and make all my sliders range from negative 10 to 10. So let's do that. So I'll just make this one change here. And going up by 1s is the default, that's fine. Actually, Actually, let's make it go up by something smaller. 0.1 is good. Okay, so there's a slider, and right now it does nothing special. I just take it and I move it to the right, and it's positive 10, and I move it to the left, and it's negative 10. I'm going to try to get it to negative 5 because I'm thinking of A as being this number over here, which for our specific equation on the previous page was negative 5. B is going to be the number touching x squared. So I just click my slider button again, and I click someplace in the blank space. And it's B, and again, we'll go everything negative 10 to 10, and we'll go in increments of 0.1. And there's B, and in this case, negative 9 is our starting one, so we're going to drag this guy all the way left to negative 9. Okay, and then finally, we're going to do one more slider for C. And again, we'll make C go from negative 10 to 10, and we'll go by 0.1s. And there's my slider for C, and we're going to take C and make it positive 2 in this case. All right, so we've got all of our sliders here. Just going to space them out. Maybe we'll shove them over on this side, actually. Okay, so there are my 3 sliders, and at the moment they have exactly the values for our particular equation. Okay, great. And so then if I just come down here and I just type exactly what the equation was on this page right here, A equals bx squared, all this stuff, the calculator, the GeoGebra is going to know I have to put a multiplication here, bx squared plus x squared plus y squared, whole thing squared. You can see it's already drawing stuff, right? It's trying to keep up with me. Here, look at that. And then times x plus c. Well, there you go. This is exactly the picture that we had in front of us, right? It's this thing in red. And so it looks good. I mean, it looks exactly like it did in the on the other picture. It looks like there's a gap here. I don't think there is. I think that either it's a graphical error or it's just having trouble. I think it's just a graphical error right there. I don't think there should be a gap. Okay, and then the equation of our tangent line we saw way down here. Where is it? Way down here, was y equals negative 1.75x minus 0.75. So here we go. First, I'm going to plot the point at negative 1, comma 1. So that's that. And then I'm going to graph my tangent line equation and hope that it sure looks tangent to that curve at that point. Negative 1.75x minus 0.75. Hey, how about that? So that right there is our tangent line at the right point. And it's all good. Okay, so I'm going to get rid of this. We're just going to play around just for a moment here with these sliders. So if I take A and I change it, remember A is the number, I can't even see the entire equation, plus it's moved it's done some manipulating to my equation, but anyway, A is this number over here, although it's moved it to the other side. It was negative 5 and it moved it to the other side to get 5. But let's see what happens to the graph. We've got 2 pieces here. If I make A negative 6. Come on now. There we go. Okay, so look, the little oval part disappeared completely out of existence right around negative 6. Just going to keep going here. So negative 10. So it's having an effect on the longer piece, sort of like making it more straight as I go this way. And then all of a sudden, as we cross roughly negative 6, the bigger piece, the oval thing kind of comes into existence. Well, they're going to like collide here. What's going to happen? So it looks like they're going to collide at A equals 0. And then, oh, look at that. Very smooth transition into this kind of wacky looking curve here. Very cool. All right, let's go back to negative 5. Let's see what happens when we muck around with B. Remember, B is the number touching the x squared right there. So let's see what impact this has. So B is currently negative 9. We'll make it negative 10. And now we'll make it less negative. Okay, then our little oval disappeared. This thing is getting straighter, straighter, straighter. Looks like it might straighten out right there around negative 1-ish, negative 2-ish for some reason. And then we keep going. Oh, look, it just flopped over to the other side. And that's kind of weird that like we get this extra stuff on the one side, but then the little oval doesn't pop into existence on the other side. And maybe if I could let B be something bigger than 10, it would pop in. I don't know. It's kind of neat to play around. And then one more thing, we'll change C. C was just this, oopsie, C was just this number right here, x plus C. So currently C is 2. We'll make C bigger first. Okay, so making C bigger like vanishes the oval part, makes this thing, it's going to crash into itself here. Oh, look at that. It just kind of separated into two different things, and then it just runs off the screen almost vertical. Look at that. And then if we make C go this way, oh, we're going to crash in again. Oh, look at that. The little oval part and the kind of vertical parts, they just change roles very smoothly, I might add. Okay, and so like I said, Geogebra is free. You can play around with this on your own. At the moment, I had 2 of them fixed at these numbers, and I messed around with the other one. But you can obviously change, you know, like what if we change A to, you know, -10, and then start playing around with B, and start playing around with C. And so there's lots of freedom that you have here to play around and graph some things that are quite complicated. So anyway, sliders I think are a really, really neat tool. You can explore using them. Okay, so if you have an equation that you cannot solve explicitly for y, like this one, then we say the equation defines y implicitly, and the technique we used above is called implicit differentiation. How do you know that we need to use this technique? The equation will have all of the x's and y's jumbled together. When differentiating implicitly, just remember, whenever you take a derivative of a term with a y in it, multiply your derivative by dy dx from the chain rule. If you're taking derivatives of things with x in them, you just do them as normal. Okay, it says here we're going to take a look at 2 Geometers Sketchpad files with 4 minutes left in class. So I'm just going to do that right now at the end of this video here. So if you have not yet done the activity, pause the video here and then come back at this point after you've done the activity. But assuming you've already done the activity and you're here, we're just going to take a quick look at 2 Geometers Sketchpad files. Okay, so the first one involves having a ladder, that's this blue thing right here, standing up on a vertical wall that's here, and then the ground is the positive x-axis. And so what we're going to do is we're going to pull the bottom of the ladder away from the wall, but we're going to make sure the ladder stays attached to the wall. So as I pull this bottom thing away from the wall, this top point of the ladder is going to slide down the wall. But we're going to pull this thing at an equal rate, we're going to move it at a constant velocity away from the wall. And it turns out that this point moves down at a not constant velocity. You might think about whether it's going to move slowly at first and then faster at the end, or faster at first and then slowly at the end, but it is definitely not constant. So we're just going to do that right now. So again, this bottom part is moving at a constant rate, but the top part is moving at very different rates. You can see it's moving very slowly here, small changes here. But as we get down to the bottom, it's going to move faster and faster and faster and then slam into the ground very abruptly. Okay, and then I'm going to show a point on the ladder. We can ignore that for right now, but I'm going to show you the symmetric ladders, pretending that there's one flipped over each of the axes. So here are 3 other ladders, and we can just imagine all 4 of them sliding around, and that's cool. So what's the point of all this? So the point of all this is that I am going to trace all of these ladders. 1, 2, 3, 4. A little shortcut on the keyboard, and we're just going to take a look at what the shape is that gets traced out by shading in all of these ladders. And if you've just done the activity, hopefully that shape right there looks familiar. We've seen it recently here in the activity. That one is called an asteroid. So that's kind of cool. So the asteroid is the envelope of all 4 of these falling ladders. That's great. Let's move this thing in closer here. Okay, I'm going to get rid of the traces. I'm going to stop tracing these 4 things. And what I'm going to trace instead are the 4 points, 1, 2, 3, and 4. And so the question is, what shape are we going to get when we trace those 4 points? So I'm doing it without the trace here just so you can get a sense of what we're looking at. So let's turn the trace on for these 4 points. And then we're going to slide this thing in, and then we're going to animate. We're just tracing those 4 points. And if you thought we were going to get a circle, then you were right. We're getting a circle because the 4 points are at the midpoints of each of my ladders. So that's cool. All right, let's bring it back here. Let's stop. Let's bring it back up here. And now I'm going to keep tracing the points, but I'm going to move the points a little bit up here. And now we're going to trace these points. So you might ask yourself, maybe pause the video here, think about what shape is it we're going to get. It's definitely not a circle anymore, as these 2 points up here and these 2 points down here get traced. And then we're going to take a look. All right, so tracing out in this case an ellipse. So the circle was actually just a special case because we were talking about the midpoints of the ladders. But really, it's always an ellipse, regardless of where those points are on the ladders. And if you wanted to, you could move the points way out here. I'm going to erase all these traces and then animate now. And so here we get another ellipse, but this one is really wide and short vertically. Okay, so that's kind of cool. And then if I stop tracing these things and I just show you the actual curve that we get, then I can show you how that curve changes. So more and more elongated ellipse here, and then becoming more and more circular until we're right around the middle. Well, exactly at the middle gives you the circle, and then more and more elongated vertically, but still an ellipse, always an ellipse. Okay, so we're going to look at one more Sketchpad thing just for kicks. All right, so let's take a look at this one. And we're going to try to describe the path that point C prime traces out as the smaller circle rolls counterclockwise inside of the bigger circle. So this circle right here is just going to roll, but it's not rolling on a flat surface. It's rolling inside of this bigger circle. So this circle is going to roll, and this point C prime is just going to go around, we say counterclockwise. So this circle right here is rolling around counterclockwise. It's rolling, and it's rolling, and it's rolling, and it's rolling. And at the moment, and I'm interested in tracing this point C prime, as this circle makes its lapse inside of the bigger circle. And at the moment, the circumference of the big circle is roughly 4 times, let's just call it exactly 4 times the circumference of the little circle, which means that this thing is going to roll around 4 times before it gets right back to where it currently is. So I am going to show you what it does, but you might pause here before I do, pause the video, and just see if you can guess what kind of a shape we're going to get by tracing this point as the inner circle rolls 4 complete times around the outer circle. Okay, so I'm going to animate first, and we're kind of watching point C prime. I'm not tracing anything just yet, but hopefully we can convince ourselves this looks reasonable. This is what we expected when I said that the inner circle was going to roll around the outer one. Okay, so now we are going to trace this point and let it run around the 4 times again. And so if you guessed that we were going to get an asteroid, then you were right. It's exactly that same shape. So it's kind of cool. The falling ladder thing turns out to be exactly the same. The envelope of the falling ladders is exactly the same as what you get when you trace a circle inside of another circle. This one right here, this shape, the shape that you get, I think is called a Hypo Cycloid. You can look that up. Pretty sure cycloid is when a circle is rolling around on level ground and you trace a point, and a Hypo Cycloid is when it's a circle inside of another circle. Okay, so that was great. So what if I changed the ratio? So what if I made it, instead of a ratio of 4 to 1, let's make it something a little bit bigger, maybe, I don't know, 7-ish. That's reasonably close to 7. So what kind of a shape are we going to get as we, again, trace this point out? But this time it's going to make 7 complete rotations before it gets right back to where it started. So here it goes. And this one is similar, but it's not called an asteroid. I think an asteroid is just that particular 4-pointed shape. But again, I think this is generally called a Hypo Cycloid. And this one has 7 points on it. That's kind of pretty. If this reminds you of an old toy back in the 80s, maybe it was popular, called the spirograph. This is exactly what a lot of the spirograph designs were based off of. The reason there's a little error over here where it doesn't quite touch is just because I didn't quite get to 7. If I was exactly at 7, this would have been perfect over here. Okay, so that seems reasonable. So what if we make it so it's not 7 to 1, but maybe we'll make it 3 to 1. So let's try to get close to 3. That's close enough. All right, so I'm just going to play it, so you won't be too surprised to learn that this is a Hypo Cycloid with 3 points, so kind of triangular but curvy. So that's fine, but the next natural place to go, we did 4 and we did 3 right here. What if I went to 2? So let's change it so that the ratio is roughly 2 to 1. All right, I think 1.99 is about as good as we're going to get. 201, fine. Okay, so we know it's going to be like another one of these Hypo Cycloids, but it's not going to have 3 points, right? It's only going to have 2. So what kind of a shape is this? I'm not going to trace it. I'm going to turn off the trace first, and I'm just going to let it play. And so we've got the smaller circle rotating around in the bigger circle. And it's going to make 2 complete rotations before it gets right back to where it started. And now we're going to start tracing. And I guess you could call this a hypocycloid with 2 points, but really normal people would just call this a line segment. And this is just totally wild to me, that you can have a round thing rolling around in another round thing, and somehow if you just watch any point on the inner circle, just pick any one you want, there's nothing special about C prime, it just goes back and forth along a straight line. That is nuts. Okay, so I think that is good. If we go back for a second to this 3-1, and I erase those, and I turn this one off, and I just show you the 3-pointed hypocycloid. I will say that that you, if you are a pro football fan, have seen. Oh, I'm sorry, it's not this symbol, is it? I think it's the 4-1. Yeah, it's the 4-1. My bad. Let's go back to the 4-1. There. And so if you are a pro football fan, you have seen this particular symbol. I'm not going to say any more other than if you go look at pro football team logos, there's only, I don't know, like 32 pro football teams or so. One of them makes use of this symbol repeatedly, actually. And there is some historical significance to that particular city and why it uses this particular symbol.